All right, let's get started. Today we are going to cover a new topic called virtual memory. This is actually a very interesting technique. It is a so-called co-design technique. So where we actually involve both hardware and software. In this case, it's a system software called OS, right? Many of you must have already heard about OS, operating system. And some of the techniques that we are going to mention here may appear somewhat convoluted at first. I'll try to slow down, right? In case you don't follow, right? In case you have a question, please do stop me. Okay. But this is a very important topic. This will help you appreciate, the complexity and also the beauty of the this memory hierarchy. Okay, common announcements. Right? Homework 7 is due tomorrow. There are actually quite a few problems, so hopefully you guys can start early. Final exam is going to be on Sunday. Okay, that's something that I already announced. May 23rd, starting from 7:30. This time we'll do we'll give you this much time. The length of the exam will be 110 minutes. Okay, almost 2 hours. I'll give you guys 10 minutes to scan and upload. Right. Same exam protocol, open book, open notes. This time it's going to be cumulative. We are going to cover the entire course. I'll talk more about how we plan to do that in a later lecture, most likely in the last lecture. Basically, how we do this in a cumulative way. Okay, and also some of you are asking, right? Also in the chat window on Piazza, how exactly do we do the ladder grading? Already mentioned, right? We are going to do a curve, and which is where we look at the median, right? So right now, here, this is the median. The red point, right? The red dot. I already mentioned that right now it's trending towards B plus. Okay, this is the, and I divided up this. This is the my grading grid, right? Each grid or each interval, right, is half sigma. Sigma is the standard deviation that you can find on Piazza. Okay, based on my experience, in the end, the standard deviation will be around 7 to 8 points. Based on the current score, it's also trending towards that, right? So which means that half sigma will be likely 3.5 or 4 points, okay? Something in that range. Okay, then per half sigma, we have this letter, right? So basically we have A minus, A plus, as simple as this, B minus, C plus, and such. Okay. All right. Hopefully this makes sense, right? This is actually very similar to most of the curve-based grading that you guys are already familiar with, and also based on my past experience, this also matches very well with the standard grading scale. All right. Any questions about the final grading? Okay, good. If not, let's move on. Let's come back to this main memory hierarchy. We have been talking about cache, right? So last time I introduced this multi-level cache system. We are using L1, right, L2 in our class, and also there's this main memory. And this is the typical size of the cache and also main memory, right? For L1 is usually in order of kilobytes, right? Just want to remind you, K means 2 to the 10, right? L2 usually in order of megabytes. This is 2 to the 20. Right? And GB, gigabytes, this is for main memory, usually in order of 2 to 30. Right? So far, we have been making some assumptions, right, to simplify our discussion. So we have been assuming that all the data our program needs can fit in this physical main memory, right, which has let's say 16 and 32, right? If you look at your current computer, or up to hundreds of gigabytes of capacity. So that's assumption that can fit. But this assumption is not necessarily true, right? Because these days we are talking about this big data era, right? Even if you look at what we are doing every day, right? We are taking photos, right? Making new videos, right? We are producing and generating a lot of data every single day, right? And this capacity is actually not enough, right? Even for a single program in many cases. And also, we have been assuming that we only look at one program at a time, right? So we assume that at any given time, our system only runs a single program, and that single program occupies, right, the entire memory space. So today we're gonna make, right, some extensions. So first, so we can ask, right, what if one program, our program, is more than the amount of installed main memory? Okay, so what if we need terabytes of memory, need terabytes of data? So how do we deal with that? And also, we're gonna ask, can we support this so-called multi-programming or multitasking, meaning that we do want multiple programs to share and reside in the same physical memory at the same time. Okay, think about it, right? So your phone is actually running multiple apps, right? There are some social network apps, right? Facebook, right? Snapchat, and there's some courseware apps like CMS, right? How can we make them coexist at the same time in the memory system? So these are the questions that we are going to try to answer in this lecture, right? So how to extend and share the main memory. Okay, hopefully the setup is clear, right? So let's first try to answer the first question, right? We talk about we don't have enough data. We want to further extend this memory hierarchy, right? And also, it's not just enough data. In fact, we have talked about this, right? So we are using, right? What kind of technology? What kind of memory technology do we use to implement the cache? Guys, SRAM, DRAM. I also asked you guys a question, right? In the prelim too. SRAM, very good. Right? We use SRAM for on-chip memory. On-chip means this memory are integrated, right, with the pipeline on the same chip. So this is the SRAM because they are fast enough, but they are very expensive, right? So that's where we don't have enough capacity. And we use DRAM, right? We use DRAM to implement this main memory. But even this one is not large enough. And also for both SRAM and DRAM, if we cut the power, if we shut down the power, it's gonna lose content, right? All the content will be gone. And in many cases, we do want to have this persistent storage, or right, there's a non-volatile storage, right? Where even after we shut down the computer, the data is still there. So that's where we actually need disk, right? This is the first time we are bringing in this disk, right? Although many of you are already using this, right? And you are already familiar with this concept, right? This is where we have could have, right, in your computer, could be 112, right, gigabytes, right, in the laptop, or 256, right? But for a larger machine, for more powerful machine, these days you can have terabytes of storage. How much is TB? How much is tera? We just talk about the 2 to the 30, right? This is GB, right? TB is 2 to 40, very good. Okay. All right. This is one thing that we wanna, right, incorporate into the memory hierarchy. So then really the natural question to ask is, how do we, right, make this work? How do we move data between, how do we swap data, right, between the main memory and the permanent disk? And also one thing to keep in mind is, right, if you go down this hierarchy, right, the access speed, right, to this storage media is gonna also decrease, okay, pretty quickly, pretty dramatically. Right, this is the access speed to the SRAM and then DRAM disk. Okay, it's much slower to access, depending on the kind of media that we use. So these days we actually have faster disks like solid state drive, SSD or flash, right? But they're still like at least 100x slower than the regular memory. And if you use a more traditional like magnetic disk storage, it's going to be 10,000x easily slower. Okay, so this is something that useful to know. Okay, so basically what we want to do is we are gonna bring in, right, so this storage to the memory system, to the hierarchy, and we are gonna be using main memory, MM, right? In this lecture, keep in mind, when I say MM, I mean main memory, and also I'm referring to the physical memory, okay, the physical main memory. So basically, we are going to use MM as sort of a cache, right, for caching the data from this permanent disk. When MM is full, since we only have limited capacity, we will have to do similar things. We have to evict some data, right, from the main memory and then move it to the disk. So that's where we have to swap data in and out, right? And this is where we can use something similar to the cache mechanism. Right? Make sense? Okay, so this is the first goal, right? We want to have access to a larger capacity. Second aspect, right? Second goal is we want to be able to run multiple programs. We want them to share the same physical memory, right? How do we do that? First, there are some requirements, some obvious requirements, right? These are actually the major requirements. So there are actually even more requirements related to speed, right, performance, and security and such. But these are two obvious requirements. So first, for a single program, right, for any given program, when it's running on our computer, right, when it's running inside our computer, it's not supposed to know what are the other programs that are being run at the same time. They're sharing the same MM, same physical memory. Does it make sense? Right? I hope this is intuitive, right? First of all, you do want this transparency, right? A program should work independently, right? Should function independently from, right, other programs, right? So the program, when you guys, let's say, many of you, right, develop apps, right? And you may develop new apps, right, in some of the other courses. When you develop this app, you are not gonna be caring about, right, who are the other developers, what are the other developers doing, whether they are also developing other apps that will be running on the same laptop or desktop or smartphone, right? You don't care, right? You only want to make sure that your program works, right? This should work independently, right? With respect to the other apps or other programs. This is so-called transparency, and also there's this protection requirement, right? Which is also the obvious requirement, right? One program should not be able to corrupt, right, or disrupt the execution of other programs, right? Make sense? Although there are, this is actually subtle, right? So there's actually performance implications, right? When we run multiple things, right, on a single microprocessor, that's something that I'm going to discuss in the next lecture. But I hope this makes total sense, right? One program should not corrupt another program. But these two seems to be somewhat in conflict with each other, right? Let me try to help you understand this sort of contradiction. To some extent, they are at odds. Okay, why is that? First, for a single program, right, it's not supposed to be aware of the existence of other programs. So that means if you look at any single program, right, or any other programs, so for all the programs, if you look at MM, right, so they're supposed to be using MM, right? So this is app 1, right, app 2. Okay, let's say app 1 is some social app like Snapchat, right? App 2 is CMS, right, the courseware. For both apps, since they are not supposed to be aware of other programs, they should have the identical view of the main memory. Make sense? Right? They should have the same view of the main memory. They should not be aware, oh, do I own this part of memory or that part of memory? They should not care, right? But the problem is that if these two programs can run on at the same time and share the same memory, and they have the same view, then it could be the case, right? So app 1 might be writing to this address, right? So whatever its address is, right? Let's say 1000 is our address. And app 2 may also choose that to write to the same address, right? Same address. That would be a problem, right? So let's say, this writing to this address really means that uploading a photo, right? For Snapchat, okay? When you upload a photo, you're actually writing data to this address. And if you're running both apps together, right, you already have two photos, right? One for a photo that you want to share with a close friend. The other photo is something, this is really a screenshot, right? Or scan for your homework. You want to upload to CMS, right? Again, app 1 is Snapchat, app 2 is CMS. And you really don't want them, right? You don't want the photo that you intend to upload to Snapchat to be mistakenly uploaded to CMS, right? That's what I mean by one program may corrupt another program if you're not careful. If you don't manage this kind of sharing in a careful way. Any questions so far about the requirement, about the challenge? Okay. Again, we want to achieve this transparency and protection at the same time, right? But there are some conflict, right? Okay, so what do we do? What exactly do we do? So basically, we cannot allow, right, both program to access the same physical memory address, right? That's a bad idea. What we have to do is we have to somehow virtualize, right? So this is the keyword. We have to somehow virtualize the main memory, where each program, they operate in their own virtual address space. Okay, so this program, they still have the same view of the memory space, but this time, the memory space is virtual, okay, for a program. And the actual physical addresses for each program, they are actually dynamically allocated and managed by the computer system. In this case, we actually need to involve, like I mentioned, both the hardware and the OS operating system. Okay, and this is our solution. So basically, each program here, again, we create this sort of illusion, right? Similar to the cache. Right? Think about cache. For cache, we are creating an illusion for the pipeline. Okay, so that this pipeline has access to something that's both large and fast, right? So that's the illusion that we create using cache. Then using the virtual memory, the illusion that we want to create for the program is that this program has access to an entire virtual memory space, okay, a memory space, and this time it's virtual. And basically, the program has its own kingdom, which is not right. It's not going to be shared with any other programs. But this is an illusion. All right. So if this is too abstract, so let's I'll show you some concrete diagram and some concrete examples soon. Again, this is the virtual memory, right? So this is the solution. We want to make use of both hardware and software mechanisms to dynamically manage the memory hierarchy, the physical memory, in a way that, right, first, we want to extend the memory hierarchy to incorporate a larger permanent storage. That's our first goal. To do that, we need to move data in and out between the main memory and the permanent storage. So think about the blocks, right? So for cache, we are moving this so-called memory block or cache block, right? So between the cache and the memory. In this case, we are moving this so-called page. I'm going to come back to this concept. We're moving a much larger block between the main memory and the storage. This is one thing that we do. And also, we create this virtual address space so that multiple programs can share the same physical main memory. And we come up with a way to protect, right? To provide protection among the programs. So even if many of them share the same physical memory. Okay. All right. So here's a more concrete view, right? And I have app A, right? Or app 1, app B, right? Like I mentioned, this could be Snapchat, right? This one could be CMS, right? But for each program, they think they own the entire address space, but this is virtual. Okay, this is an illusion. This is a virtual memory, and this address. Okay, in this example, right, each application, let's say we just start with a virtual address 0, so they can write and read from any addresses in this virtual space, okay, from 0 to certain range. Right, but of course, right, this is just an illusion. We still need to implement this virtual memory somehow using the physical main memory in DRAM, right? What actually happens is, so really, app A and app B, they are actually sitting in different physical memory address ranges. Okay, like for example, app A is sitting here, part of app B is sitting here. Also, we don't have to load all the data and all the instructions for app A at the same time into the physical main memory. Why is that a feasible choice, guys? In fact, in many cases, we just need to load a small chunk of data and small chunk of instructions into the physical main memory. And the program will be running happily for a while. Very good locality, right? So there's a principle of locality. Same thing here. Okay? Just like how we exploit the locality for cache. Same thing here. This is basically cache, right? It's a main memory basic cache for the storage. We usually use a small chunk of data for a while before we move on, right? We have this temporal and spatial locality. Okay, right. Again, without the VM, right? Without is a virtual memory, app A and app B will fight with each other, right? For the same address space. So that's something that we want to avoid. Okay. All right. So now that I've introduced, right? So there's a virtual address, a virtual address space, physical address. What exactly do I mean by that? So by virtual addresses, I really mean the addresses used by the program. Okay, when we are running a software program, when we're running those instructions. So the address in those instructions, whether we do load or store, and also the address of the instruction itself, now they are virtual. Okay, keep this in mind. This is really important. So for any modern system, computer systems, these addresses are virtual. Okay, these are not the real addresses. When you are running an instruction at address 0, okay, that address 0 is virtual. That does not necessarily correspond to physical address 0. Okay, keep this in mind. Everything's virtual, and with the n-bit virtual address, so of course, right, we can address 2 to the n, right, 2 to the n. These days, actually, we usually have 32-bit, right, address or 64-bit address, right, for modern computers. So let's say we have 32-bit virtual address. Virtual address. What is the virtual address space, guys? 32-bit. That's 2 to the 32, right? What is this? In terms of GB. Very good, right? 2 to the 2 times 2 to the 30. We already know that this is G, right? GB. And the byte addressable. This is 4 GB. Right? That's the address range. And these days we usually have 64-bit, right? System, right? When they say 60-bit, it's really the address and also the word size, right? 60-bit, usually we don't use all the bits, right? 60-bit, 64 is a lot, right? To address a large space, very large space. We usually use a part of the bits, right? For the virtual address space. And physical address, this is real address used by the hardware. Okay? When we actually access the physical memory, we need to use the physical address, right? Same thing here, we need address, right? But now we need to distinguish physical address from the virtual address. And let's say the physical address has n bits, okay, n bits. We can access, right, to the m number of bytes in the physical address space. And usually m right? The physical address is shorter than the virtual address, right? For a good reason. Just like cache, right? Cache is smaller than the main memory. In this case, right, the actual physical address space, right, is of course smaller than the virtual one, because the virtual one is just an illusion. Any questions so far? If not, let's talk about paging, right? I already mentioned the notion of page, the concept page, right? This is a virtual and physical address space. They are usually divided into the so-called equal-sized pages. And each page has certain number of bytes, right? Usually, of course, right? So in our, right, in the computer, right, digital computer, everything is power 2, right? Internal address, right? Everything power 2. And typically, the typical page size is this number. What is this number, guys? In terms of K, what is the shorthand? 1496. You know, we have played this game, right? 2048 months, 4K. 4K capital B, 4K bytes. Capital B means byte. 4KB, 4 kilobytes. And we want to read the whole page, okay, in and out. Why is that? What kind of locality are we exploiting? Spatial, right? Mostly spatial. Same thing here, right? Same, just like a cache. We want to read the whole block because most likely the data nearby will be used as well, right? So that's the size of the page, usually 4 kilobytes. And once we have this the notion of page, then we can actually index the pages, right? So of course, all the addresses are byte addressable, but now that we have the notion of page, just similar to cache, we have the notion of memory block address, right? Cache block address, right? Over here, for virtual addresses, we have something called virtual page number. Each page has 4 kilobytes. That's a typical size, okay? Unless, you know, I define it in right, differently, right, in the exam or homework, right? So usually in modern system, usually we have 4 kilobytes. And this is so-called VPN, right? For virtual page number, we have something called VPN. This is not the VPN you guys use, right, to access the Cornell network. This is really for the page number, okay? VPN. And for physical page number, we have something called PPN. Again, I have thrown a whole bunch of definitions, right, to you guys. So here's a more concrete view of the virtual address. Also virtual memory. Okay. We just talked about this, right? Let's say we have 32-bit virtual address. We can access 4 gigabytes of a virtual memory space. Okay. This is the first. This is virtual, right? And given the right, so the notion of page. Now that we can divide this virtual address space into many pages, right? Each page has 4 kilobytes, right? Basically 4096 bytes per page. And this is my page 0, right? This is where I have this VPN, right? I said VPN is 0. Virtual page number is 0. And I can just name or index all the remaining pages, right? So just want to make sure that you guys pay attention to the indexing, right? So the address start from 0. So that's where the first page, right, ends at this address. This may be related to one of the quiz later on. Okay. 4095, right? So this is the last address, last byte address for the first page, page 0. How many pages do we have? Right? We have many pages. In this case, we have 4 gigabytes, right, of virtual memory space. Each page is 4 kilobytes. How many pages do we have in total? Numbers very good. 2 to the 20. What is that? Let me put it here. 2 to the 20. What is that? In terms of K, M, G, right? Kilo, mega, giga. Okay, you guys really want to be familiar with this, right? We have roughly 1 million pages, right? 1 million pages, not bytes in this case, right? We have this many pages, right? Roughly 1 million pages. All right. Any questions about the VPN? How we do the virtual addressing? Right. So basically, this is a view for a program. Right? The program sees these virtual addresses. Of course, we need to somehow translate this right into the physical addresses. But let me ask you guys one more question. Per page, right? Per page, for each page, we also want to address. Let us say we want to address the bytes inside that page, right? Your 4 kilobytes. So how many byte offset bits do we have per page? Simple cache, right? We have been asking guys the same question, right? If we give you a block size of 8 bytes, right? We have 3 byte offset bits. Right? Same thing here. I can ask you the same question. Now I have 4 kilobytes of page size. How many bits do I allocate to address the bytes? Very good. This is right. This is 2. This is 4 times. Let me be clear. 4 times 2 to 10, right? Which is 2 to 12. 12 bits. Good. The 12 bits in the virtual address will be allocated for the byte offset. And the other 20, right? So this is something that we just agreed on. We have 2 to 20 number of pages. So 20 bits in this case. We have 20 bits for the VPN. All right. Okay. So now that we have the virtual address space right over here, so this is a virtual address space, and we have the physical main memory over here, right? So one thing that I want to emphasize is, okay, over here, we have these pages. So each one of this is a page. Okay. Per page, right? Per page, we will need to come up with a mapping scheme. We will come up with an address translation scheme. Because per page, right, we have this VPN, right? For each page, we have the VPN, that's a virtual address. So eventually we need to translate it to the PPN, the physical page number. So how do we come up with that address translation? That's something that we need to discuss. But usually what happens is, okay, when we request a page, right, when we try to access a page, a virtual page, so we need to first find out whether that page is already in the main memory or not. Okay, there's some sort of mapping. It's not in the main memory, then the OS and hardware will be at work and then try to load that page from the disk. This is the hard drive or hard disk to the physical main memory. Okay. And then save the correspondence. So the OS and hardware will need to come up with some sort of address translation scheme. Okay, so basically per virtual page, right? Per virtual page, we need some kind of address translation to translate it to the physical page number so that we can actually access the main memory. It may not be in the main memory. If it's not in the main memory, then we have like this one, the gray one. This is actually where we have a invalid page, okay, page entry. So which means that this is not brought into the main memory yet. So the data, the corresponding data is still on disk. Okay. But really the question is, right, so how do we come up with this kind of address translation? So that's really the next problem that we want to resolve. Is the overall setup clear so far? We have some virtual memory, right? And they will be, so these addresses will need to be translated into some physical main memory address. We do this translation for each page. Okay, in case this is still too sort of abstract, right? Let me try to give you guys an analogy, right? We have been trying to come up with some use analogy for the important concepts. Or maybe I can ask the class, right? This time. Have you seen this kind of a virtual paging system in your daily life before? Does it ring a bell? Any analogy that comes into your mind? Right, this is not as straightforward as the cache, right? And also the pipeline. So let's say, in fact, we are using, we're actually using this notion of page, right? So now then let's just look at the book, right? This is a Harris book. Okay. I don't know how many of you have the physical copy, the hard copy of the book. It's actually a pretty heavy book, right? But in most cases, you don't really want to carry the entire book around, right, in your backpack. That's just too heavy. So ideally, when you are reviewing the cache chapter or the virtual memory chapter, you want to be able to sort of unbind the book, right, and just take out the related pages. Is that right? And put it somewhere. Okay. So basically, this is the book, right? And you want to put it somewhere, right? And you may actually have many books, right? Because you're taking many other courses. You may want to do the same, right, for other textbooks. Okay, you'll take out a few pages from book one, like in this case, Harris book, and you take on some pages from another book, and you combine them somewhere, right? Right, you'll make a super book. What is the name, guys? What do you use to organize? Not quite, right? Very good. Okay, right? This one, right? Binder. This is something that we use a lot, right? Okay, we talk about the book, right? We have a book, and we have this is a ring binder. Right. These days, of course, everything's getting virtualized, right? The binder can be also virtualized, right? With an app. And which one is the virtual address? Right? Which one is the virtual memory space? Which one is the physical memory space? What is this? The book? Very good. The book is the virtual memory, right? And binder is the physical memory. Make sense now, right? Okay. But then the question is, right? How do you, once you put these pages, right? Really, literally, we are using a paging scheme over here, right? So that's why I really think this is a very good analogy. And what do we do with the translation? Actually, this is a real binder that I own. So this is something that the College of Engineering gave me when I serve as a freshman advisor. Okay, for the I have a class of advisees, right? See here. Okay, so this is how we organize, right? Because we may have different pages from different books, right? These books basically correspond to the app, right? Different book correspond to a different app or different program. I mean, to somehow come up with the address translation, we want to be able to quickly find, right? For book one, right? Harris book, where can we find the pages, right? The corresponding pages in this binder, in this physical memory. So we need this TOC, right? Table of content, right? So that we can quickly we can quickly find the corresponding pages. So what exactly is TOC, right? What is this? How do we implement this kind of a table of content in our virtual memory? That's the next question that we have to ask. And actually, this is just a lookup table, right? We just implement some kind of lookup table to implement this kind of TOC. All right. Does the analogy make sense? Any questions? Hopefully this gives you a much better understanding, right? Of also make you much more comfortable with the virtual memory. It's not like, this is not something that we only use in the computer system. This is something that we also use a lot in our daily life.